All right, geometry students, this is section lesson 8-3, tests for parallelograms. It's located on page 322 in print and page 322 in Braille, straight up 322. Lesson 8-3, tests for parallelograms. So you have learned, in 8-1 about quadrilaterals, and in 8-2 a bunch of theorems that apply to parallelograms. Now we're going to go backwards with those theorems. We're going to use converses with those theorems to test quadrilaterals to see if they can be identified as a parallelogram. And you're going to use your deductive reasoning and your knowledge of those theorems to prove it, to state the reasons why things happen in order to make it a parallelogram. And not only are you going to tap into the previous theorems in just the last two lessons, you're going to tap into knowledge and theorems and definitions from way back into chapters 2, 3, 4, 5, 6 in regards to definitions of bisectors, vertical angles, transversals with parallel lines, and alternate interior angles that are congruent. Just all that knowledge. The knowledge from triangle congruency with angle, angle, side, angle, side, angle, side, angle, side, 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 side. You've got to pull that information up forward in your brain and think about it, because you're going to use it in this section to prove whether a quadrilateral is a parallelogram or not. So on the first page, it talks about what you'll learn, and then there's a paragraph that talks about theorem 8-3, states that the opposite sides of a parallelogram are congruent. You just learned that. Can the converse be also true? Or if it's a parallelogram, then the opposite sides are congruent. So we're going to state that in a theorem, a couple pages in Braille. So move to 323, and turn to theorem page 323. We're going to state the converse. It says theorem 8-7 on page 323. If both pairs of opposite sides of a parallelogram are congruent, then the quadrilateral is a parallelogram. And they have a parallelogram and a model here with tick marks showing congruency of the opposite sides, and then in symbols down below the parallelogram they also state that the sides opposite each other are congruent. So if a parallelogram, R is in the top left corner vertex, S is in the top right, T is in the bottom right, and U is in the bottom left. And then we go back up to R again. So we have a four-sided figure. We know it's a quadrilateral. Then on the top side, RS, there's two congruency tick marks. On the bottom side, TU, there's two tick marks. On the left side, RU, there's one tick mark. And on the right side, TS, there's one tick mark. And in symbols, it says RS is congruent to UT. Notice they use corresponding angles to name their sides. RS is congruent to UT. Oh, they didn't on this one. Interesting. Never mind. I take that back. I would have probably said TU because R is opposite T. And then RU is congruent to ST. And you can use the properties of congruent triangles in this theorem to find other ways to show that a quadrilateral is a parallelogram. So that's the next example, walking through a proof of showing that a quadrilateral is a parallelogram from all the previous knowledge that you have obtained, using logical step-by-step deduction to prove this, to argue it, to present it to somebody other than it just looks like a parallelogram. It is a parallelogram. You can't say that. You have to deduce it. You have to logically argue it. So on the next page, 323A, they give you some givens in example 1. It says, in quadrilateral ABCD with a diagonal BD, AB is parallel to CD, and AB is congruent to CD. This is where I want to notice that they name it by corresponding parts. AB, and then they name it CD because A corresponds with C, B corresponds with D. Show that ABCD is a parallelogram. So they have a drawing, A in the top left, B in the top right, C in the bottom right, D in the bottom left. That is our quadrilateral if we join all those vertexes. So that's the first statement they gave us, is that ABCD is a quadrilateral. Then they also stated that BD is a diagonal. So notice from the top right all the way down to the bottom left, we have a diagonal going through the midst of our parallelogram, joining the two opposite angles, B and D. They say AB is parallel to CD. Notice the top side AB has a parallel indicator with that little arrowhead, and CD has a parallel indicator down at the bottom. So it's showing in the drawing what it's giving to us in writing, that AB is parallel to CD. And then they're also saying AB is congruent to CD. There's a congruency tick mark going through AB and a congruency tick mark going through CD. So we think about all this stuff. We know that AB is congruent to CD, and we know that AB is parallel to CD, and AB is congruent to CD. So that's the first start. We're like, oh, okay, cool. We know that we want to show that ABCD is a parallelogram. So it details down below in a plan that one way, there's other ways to show this, but one way to show ABCD as a parallelogram is to show that AD, so the left side, is congruent to CB, the right side. Because if we show that the opposite sides are congruent, we're using the converse, we're using that theorem that uses the converse that says opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So we want to show that. And we could show that by showing that the triangles that are created by this diagonal going through the midst of it, notice from B to D, we've got a diagonal that creates two triangles. If we show these two triangles are congruent, then we're going to be able to show that all the sides are congruent, or the sides of the triangles correspond to each other, are congruent, and therefore opposite sides are going to be congruent. And we can show by this theorem that this is a parallelogram. So the next page details a very traditional proof going through the process. And you got to read the lines of the proof and then go look at them in the drawing and think about them. So on the next Braille page, 323B, the first step, number 1, under our solve, is they detail that angle ABD is congruent to angle CDB. So if you go back to your drawing, and you find A, B, D. A is in the top left, B is in the top right, D is in the bottom left. ABD, that angle is that top little angle above the diagonal. And then they say that's congruent to CDB. So down at the bottom right, C, to bottom left, D, and back up to top right, B. The angle that's created there at D on the other side of the diagonal. Those two are congruent. And why are they congruent? Well, that BD line, that diagonal, is a transversal, isn't it? If we extended it up into infinity top, extended it down into infinity bottom, AB and CD are parallel lines. That BD is a transversal. Thinking way back to when you learned about parallel lines and transversals, that transversal is creating alternate interior angles. So that ABD angle up there at the top is on the one side of the transversal, and the CDB angle at the bottom is on the other side of the transversal. So they're on alternate sides of the transversal, and they're on the inside of our parallel lines. So they're alternate interior angles. So that's the reason they're using, is you go back to your proof, and it says if two parallel lines are cut by a transversal, then each pair of alternate interior angles is congruent. Alternate interior angles of parallel lines are congruent. So number 2 says an obvious one. The reason why we have to say this, I'll explain this. It says BD is congruent to BD. And you should say, well, duh, 2 is congruent to 2, 3 is congruent to 3. Why do I need to say BD is congruent to BD? The reason why we have to say it is because we have to use it twice. So if you go back to the diagonal BD, BD is part of the triangle on the top, ABD. And BD is part of the triangle at the bottom, CDB. So we have to say BD is congruent to BD because we want to make sure that in our argument that we're clear that the side of this triangle, ABD on the top, is congruent to the side of the bottom triangle, CBD on the bottom, or CDB on the bottom. You have to say that. You have to make it obvious to the reader that we're going to use this side twice because we want to show that triangles are going to be congruent to each other. So we're setting up a side angle side situation. So we have to say BD is congruent to BD, and we get to say that by a very simple property called the reflexive property. And we just used it. It's kind of like just a little quick step to remind the reader, to remind the person that we're trying to prove this to, that we can use this side twice. 2 equals 2. We're going to use it twice. BD equals BD, reflexive property. Then in number 3, they state a given. AB is congruent to CD, and that's given because they gave that to us in writing at the very beginning of the problem. They said AB is congruent to CD. They gave it to us in the drawing. The top side is congruent to the bottom side with tick marks. So we get to say given. That's always fun to be able to list out some givens and just say given. Then number 4, it says triangle ABD is congruent to triangle CDB. And the reason why we get to say that is SAS, side, angle, side. If you go back to your drawing, we have the side at the top. We have the angle up there at ABD at the top right, because we already said that angle is congruent to the bottom one, CDB. And then the side, BD, the diagonal, is going to be congruent to itself, to the next triangle. The bottom triangle, we have the bottom side, CD. That's congruent to our AB. Our angle, CDB, we already determined is congruent to ABD by alternate interior angles. And then our side, our diagonal BD, is congruent to itself. So we have a side angle side situation proving these two triangles are congruent. So then the next step, turn back to your proof. Step 5, this taps into a piece of information we used a long time ago. It's probably like you're going, oh yeah, I think I remember it. We got to use it again. It says that AD is congruent to CB. Well, think in terms of triangles. If we just said that one side is congruent to another side, and one side is congruent to the other side, and an angle is congruent to the angle, we proved they're congruent angles. So now we get to say every swinging thing is congruent to each other. So instead of labeling all the angles because we don't care, we want to prove the sides because we want to be able to use our parallelogram theorem about opposite sides are congruent. So we use the AD is congruent to BC because it's a side of a triangle that we already said is congruent to another triangle. So the sides have to be congruent to each other. So we have to state that. We have to say AD is congruent to BC. And the reason why we get to state that, turn back to the page, is this interesting little acronym, CPCTC. It stands for corresponding parts of congruent triangles are congruent. So if you prove that two triangles are congruent, you get to say all their corresponding parts are congruent to each other. Duh. But we have to state that. And we wanted to state that these two sides are congruent to each other because we want to build a case that all 4 sides, the opposite sides, are congruent to each other so that we can use Theorem 8-7 to say this is a parallelogram. And that's exactly what we do in the next step. Step 6. ABCD is a parallelogram. Why? Because of Theorem 8-7. You'd write this out a little bit more than just the numbers. You would say if both pairs of opposite sides of a parallelogram are congruent, then the quadrilateral is a parallelogram. Well, we were given that one set of sides was congruent, and we just proved by proving alternate interior angles are congruent, that sides are congruent, by side angle side 2 triangles are congruent. So then their corresponding sides are congruent. So now we have all the sides. We have both pairs of sides being congruent to each other. So now we're able to use this theorem to say that it's a parallelogram. There's just one way to prove it. We could have proven by sides, angle side side. We could have said, well, we've got a side. We could have said, we've got another angle, the angle not included, and a side and a side angle. Or we could have proven alternate exterior angles. We could have used lots of different things, but we chose to just go this route. All right. In the Your Turn on the next page, they give you another quadrilateral to look at. They give you some givens in writing. Then they list out the steps. They're very nice in that they list out the steps and the symbols, and you have to decide upon the reason why they gave that step. So it says, in quadrilateral PQRS, PR and QS bisect each other at T. Show that PQRS is a parallelogram by providing a reason for each step. So first take a look at your drawing. P, Q, R, and S. P, Q, R, and S. You got top, left, top right, bottom left. P, Q, R, S. There's a quadrilateral. We got a four-sided figure. That was given, that it's a quadrilateral. Didn't tell us it was a parallelogram, though. We have to prove that. So, but it did say from P to R, so from opposite angles, P to R, and Q to S, they bisect each other. Aha! We should be putting in our brain, what does bisect mean? Learn some things about bisecting diagonals of parallelograms. They also show it bisecting at T in the middle, and then from P to T, top left to the middle, there's a tick mark, and from T to R, there's a tick mark. And then from Q to T, top right to the middle, there's two tick marks. And from T to S, there's two tick marks. So that's showing that they bisect each other. That's showing congruency. Bisect means what? Divide in half. Dividing in half means we have equal parts, right? So the first statement they make in little letter A, down below your drawing, is that PT is congruent to TR and QT is congruent to TS. Why is that? Why does that happen? Well, we were told they bisect each other. So by definition of bisector, we know they're equal to each other. So we just say definition of bisector. Little letter B says that angle PTQ is congruent to RTS. Oh, interesting. So P top left to the middle T, back up to Q in the top right. That angle there in the midst is congruent to STR, that angle there in the midst. Well, what kind of angles are those to each other? They're directly opposite each other, sharing the same vertex. So they're vertical angles, and vertical angles are always congruent. They're also going to state that the other two angles, STP, bottom left to the middle to the top left, STP, is congruent to RTQ, or QTR, directly across from each other, right in the middle, sharing the same vertex, vertical angles again. So we've got another pair of congruent angles. So we're proving, okay, congruent angles in the midst here by vertical angles. Vertical angles are congruent. That's our reason. Little letter C, they say, well, now I've got triangle PQT, so P top left, Q top right, T to the middle. I've got this little top triangle up there. That's congruent to triangle RST. Okay, well, yeah, because of why? Well, I've got a side congruent to a side, and an angle congruent to an angle, and a side congruent to a side. This is because of SAS, side angle side. They also state the two triangles on the left and the right, PTS and RTQ. Those two triangles are congruent to each other because of side angle side. So if I've got that going on, then I'm able to say, well, shoot, then PQ, the top side, is congruent to RS, the bottom side, because of corresponding parts of congruent triangles have to be congruent. If I've got two triangles, those two sides have to be congruent also. And then I also state that PS on the left is congruent to RQ, QR on the right because of the same thing, CPCTC. Corresponding parts of corresponding triangles of congruent triangles are congruent. So now I've proved all four sides are congruent to each other, or congruent pairs. So then I get to say, because of theorem 8-7, if both pairs of opposite sides of a quadrilateral are congruent, then it's a parallelogram. And that's the little letter D, theorem 8-7. Right? So there you did a proof. They gave you the steps. You had to say the reasons. You had to really think about and tap into the knowledge that you already know about vertical angles and side angle side, and then corresponding parts of congruent triangles are congruent. CPCTC. All right. Turn the page, Braille page, turn the print page. This leads us to two more theorems, because we then now just proved a bunch of stuff. We can create a couple theorems. There's a page break. It says theorem 8-8. If one pair of opposite sides of a quadrilateral is parallel and congruent, then the quadrilateral is a parallelogram, right? And we just proved it, because if we drew a diagonal and we'd have CPCTC, we know that the sides have to be all sides have to be congruent. So we only need one pair of sides, and we know that we've got a parallelogram. We don't need both pairs, we just need one. So you have a parallelogram A, B, C, D in a drawing. A's top left, B's top right, C's bottom right, D's bottom left. And they show that AB is parallel. The top line segment is parallel to the bottom line segment. You've got a parallel arrow indicator. And then they show a congruency mark. We know that if we're given that AB is parallel to CD and we got a congruency mark, that we get to say this is a parallelogram, because if we went back and drew a diagonal and did all the proving of things, we would prove that AD is congruent to BC. So we're golden. In symbols, it says AB is congruent to DC and AB is parallel to DC. The next theorem shows the bisectors with your diagonals. So theorem 8-9, so it's the converse of a theorem that you already learned in the previous section. You learned that if a parallelogram has, the diagonals of a parallelogram bisect each other. Now we're going to say it backwards. The diagonals of a quadrilateral bisect each other, then it's a parallelogram. So that's what it says in writing. The diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. It's a converse of a theorem you learned last section. So we have A, B, C, D again. A is top left, B is top right, C is bottom right, D is bottom left. And then we have two diagonals going from our opposite angles, so A to C and B to D. They're at a point E in the middle. From A to E is 2 tick marks, and E to C is 2 tick marks, showing that they're congruent. From D to E is 1 tick mark, and B to E is 1 tick mark, showing they're congruent. So showing they bisect each other. We just proved in a your turn proof that with vertical angles and CPCTC with side angle side, that we have a parallelogram. So we don't need to go through that proof anymore. We're able to just say, hey, if I know I've got these two diagonals running through this quadrilateral and they're showing congruency, they're showing that they're bisecting each other, I know this is a parallelogram by theorem 8-9, that if two diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. And in symbols it says AE is congruent to EC and BE is congruent to EB. So then in the examples, you decide based upon these theorems whether a drawing is a quadrilateral or not, or a parallelogram or not, whether a quadrilateral is a parallelogram or not. So in example 2, it says determine whether each quadrilateral is a parallelogram, and if it is, give a reason. So we have this parallelogram figure, four-sided figure, quadrilateral, and we're going to try to see if it's a parallelogram. So it doesn't have any labels on it, it's just a four-sided figure. But it does have tick marks. It has 1 tick mark through each side. So that's showing that all four sides, opposite sides, are congruent, aren't they? So why is this a parallelogram? Well, we get to use that theorem that says if opposite sides of a quadrilateral are congruent, then it's a parallelogram. So that was simple. That was just, boom, we're done. That's what it says down at the bottom. The figure has two pairs of opposite sides that are congruent. It is a parallelogram. All right, turn the page. You have another quadrilateral. Four-sided figure. They haven't labeled any of the vertexes. They've just done this interesting looking four-sided quadrilateral. We have a tick mark in the top, a tick mark on the right side, so those two sides are congruent. Two tick marks on the bottom and two tick marks on the left. Those sides are congruent. Is this a parallelogram? Hopefully you're saying no. Why? Don't say because it doesn't look like one. You can't say that. You are a Euclidean geometry attorney. You have to say why this is not a parallelogram. What's interesting, it has two sides that are congruent, but there's no theorem that says any two sides that are congruent. It says opposite sides have to be congruent. So the top has to be congruent to the bottom side. The left side has to be congruent to the right side. It's not that way. The left side is congruent to the bottom side. The right side is congruent to the top side. This is just a kite, I think. Like you kind of tip, sideways and look at it. It's not a parallelogram. It's quadrilateral. It's not a parallelogram. So this is not a parallelogram. Right? Try on the next one on the your turn. There's two drawings on page 324D. So little letter F. We have a four-sided figure. You make your way around the figure in each vertex. And then notice that from opposite vertexes there's diagonals. They intersect each other. They better. Two lines always intersect at a point. From the top right to the bottom left, there's a tick mark going from the top to the middle, and then a tick mark from the middle intersection point to the bottom left. Okay, that's showing some congruency. And then from the top left to bottom right, it's doing it again. Two tick marks from the top to the middle, and then two tick marks from the middle to the right. So it's showing congruency. So your brain kicks in and you go, ooh, these diagonals are bisecting each other. So by the theorem that says if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. This one is for sure a parallelogram, just knowing that the diagonals bisect each other. The next drawing, number 9, we look down at this drawing, and we've got four sides. We've got a diagonal going from top right to bottom left. There is a tick mark on the top side, a tick mark on the bottom side. There is two tick arcs at the top angle to the right, just above the transversal, the diagonal. I gave it away, didn't I? And then two tick marks on the bottom left, just below the diagonal. This should look familiar. We just proved this. We have this diagonal with these congruent alternate interior angles. Therefore, this diagonal is a transversal of parallel lines. So we know the top and the bottom are parallel because this diagonal transverses it and creates these congruent alternate interior angles. So we know we have parallel lines and we have congruent lines. So by theorem 8-8, if you have opposite sides that are congruent and opposite sides that are parallel, you've got a parallelogram. Now, they didn't put a little parallel indicator on the top and the bottom. We had to think about it and go, oh yeah, that diagonal is a transversal, and it's created alternate interior angles, and those alternate interior angles I'm being told are congruent. Therefore, then I know that the line on the top and the line on the bottom are parallel to each other without even a mark. So if they're parallel and congruent, I have a parallelogram. All right, see how you got to really deduce and think about and use your logic and argue, why is this? Don't just say it looks like it. Okay? Really think about the reasons that you've learned and why you're able to say that it is a parallelogram. Okay? All right, that's the end of section 8-3. And there's some check your understanding. It'd be really good to do page 3 25, at least number 3 through 6. But for extra practice, I would go all the way 3 through 13 to work on it. If you're not doing them in class with us, you should be doing them on your own to really practice these concepts. So that's it for 8-3 tests for parallelograms. Keep that brain engaged and turned on doing good thinking. Thinking about the reasons why. The Euclidean geometry reasons why. You're geometry attorneys. You're arguing to the court, to the judge, why these things are such. You can't just say because they look like it. You can't tell the judge, well, the criminal looks innocent, so let the criminal off. Or the criminal looks guilty, put him in jail. You gotta say why. You gotta prove with evidence, with statements, with conjectures, with givens, with definitions and properties, the theorems and the postulates, why something is so, and do it in a logical way. And that's what you're learning to do. You're learning to prove this stuff in a logical way. Super important skill to have for many math classes, and then quite frankly for real life. You become a really good debater. You become a good presenter as to why something is such. Why is it so? What are your reasons? What's your logic? How can you argue this point and prove it? Win it if you need to. All right? So that's it. We'll head on into 8-4 in the next video. Do good thinking.